Okay, so thank you for your attendance. Let's welcome our today's RS speakers from Stanford University, Professor Reinhold Darkstad, and his Ruth and William Bors Professor in Material Science, Mechanical Engineering, and Surgery. And he's from Perovskite. Today, he will talking about the perovskite in this afternoon. His presentation title is Open Air Spray Plasma Manufacturing of Large Area Perovskite Solar Cells and Modules. So first, let's thanks Professor again. Sorry.
Well, thank you. It's great to be here in this room again. And I'm going to use a few slides that I used in my talk this morning, because some of you were not there this morning, but some of you are here again. So please excuse the repeat. But this is the front of Stanford University. And this is the original main quad that was built in the late 1800s. This is the main church over here, and it used to be twice as high, but in the 1908 earthquake, it was basically destroyed, and so this has been rebuilt. It looks very tranquil. It looks like a club, but in fact, it's, as I'm going to show you, nothing like that at all. The campus of Stanford University is very large. It's over 8,000 acres, so that's extremely big. We have about 600 buildings. We have our own power plant, 49 megawatt power plant, which has got a large component of renewable energy sources. So we're self-sufficient in terms of power. We have a large shopping center, which is one of the highest grossing shopping centers in the entire Bay Area. That's not because students and faculty shop there, but it's a big place. There's, let's see here, we have the Stanford Linear Accelerator Complex, which is a large beamline with X-ray scattering and other coherent light sources that we use quite extensively in our research. So there's a lot of facilities, and you see here a picture. The picture I showed you was this front facade over here, but as you can see, the entire campus actually is this entire region over here, going all the way up around here. So it goes right up into the hills behind the university, and this is the linear accelerator complex over here with all of the beam stations down over the beam lines down over there, where we do a lot of work. We have a golf course, a shopping center is this whole region here, and then several hospitals are on campus as well. So this is the university, and if you look at where we are in the San Francisco Bay Area, here is San Francisco itself. This is the Golden Gate Bridge right over there. And then going down the peninsula, this is where Stanford is located, and in fact goes all the way up into the mountains over here. And this is sort of the northern tip of Silicon Valley. So as many of you would know, Stanford is really deeply connected with many different industries, and has really been significantly involved in entrepreneurship and innovation, and that continues. So many of our programs have connections with the Valley. And as I mentioned this morning, the Valley is no longer just a physical valley. It's really a virtual valley in many senses, and it extends all over the world. And then coming up on the East Bay here, this is the Bay Area. Coming up on the East Bay, you get up to Berkeley over there, and as you would know, there's a small public institution there. Okay. So what I want to talk to you about today is our work on open air spray plasma manufacturing of perovskite cells and modules. So the focus of our effort has been on manufacturing, scalable manufacturing, nominally in open air. And by open air, I don't mean in a controlled inert environment. I mean in actual open air. Of course, you have to control for particulates because we're making very thin films. But other than that, it's really devices that are made in California open air. And also on their stability. So those are the two main themes that I wanted to talk about. And you can see here an example of the initial ultrasonic spraying of precursors for different perovskite compositions, which we then follow with a plasma source that very rapidly cures the perovskite layer. So here's an example of a perovskite cell. This is an Elbeck image. It's about 1 centimeter wide and 10 centimeters long. And that can be manufactured fully in open air and done very rapidly. And you can see here is a mini module that was made. This was an effort jointly with NREL, who has a program called PACT. And the PACT program is looking at developing new accelerated testing capabilities and standards specifically for perovskites. And so we have been part of that. In fact, we delivered 50 of these mini modules to PACT for testing. I'll mention this program again a little bit later on. So here, let me acknowledge the students and postdocs that have been involved in this work. These are my current PhD students working in this area, and former members are listed over here. Many of them now, some of them have gone on to become faculty members like Adam Prins, Will Scheidler, and Nick Ralston. The others have graduated and moved on. We also have a number of undergraduate students working in this area, and I acknowledge the support we've had here from both government sources as well as some Stanford funding as well. I know there's people in the community here that are working on perovskite, so you know this message. But for those of you who don't, this is a plot. Here is the date coming up to current time, somewhere around about over here. And these are the efficiencies that have been achieved in different solar absorber technologies. And you can see crystalline silicon out over here really beginning to plateau sort of after the mid-1990s. And, you know, this always inches up by small amounts. Here's organic photovoltaics. And this is an area that I, along with several faculty at Stanford, had some programs a number of years ago. And you can see their improvements in efficiency. The problem with the organic photovoltaics is that they were really never very stable. They like perovskites, continue to have stability concerns, but they were also expensive. And their efficiencies, well, there's been improvements more recently, but around about the time that there was a lot of programs in organic photovoltaics, their efficiencies just weren't that great. So funding then starts to stop in OPV systems around about 2010 to 2015, but along comes perovskites. And then nearly everybody who was working in organic photovoltaics now jumps into the perovskite area. And now it's standing room only in the perovskite sections, and there's fewer people in the organic sections. But for good reason, you know, as you can see here, and as you would know, and this is not the records that we have anymore, there's still improvements on this, the efficiencies are actually very impressive of what's achievable. Plus, it's solution processing. So unlike crystalline silicon, where you really are dealing with much more slow and expensive manufacturing, the potential here for solution processing of perovskites is really tremendous, as it was for organic photovoltaics. Other benefits of the perovskite is that they're very good, very efficient absorbers. So strong absorption. You can make it 1,000 times thinner than silicon, so there's much less use of materials. Excellent but tunable band gap depending on composition, good efficiencies, a large risk, a tolerance to defects and impurities, grain boundaries, which again is not something that you typically see in silicon solar production. Plus, as I mentioned before, it's potentially easy to make, so with solution processing. So what's the challenge? Why aren't we painting buildings and painting our children and with perovskites and generating energy everywhere? The problem is that as you scale manufacturing, there is a penalty in terms of efficiency. Now, this is nothing new. I've done a lot of work over many years in the semiconductor industry. The same thing happens there. You can have pathfinding for a new processor, and you can try to figure out as many of the defects and defect distributions. But the minute you start scaling to thousands of wafers a week, that's when you start seeing the manufacturing defects, and that's when you start seeing the penalties in terms of efficiency. So the same thing is true for organic photovoltaics, for perovskites, and even for silicon. So as you increase the active area, you see this decrease. So this has been the motivation for part of our work, is how can we do this manufacturing but actually improve the efficiencies, move in this direction here. So all of our work is done with scalable processes. Spin coating is not scalable. Of course, we, like many other groups, use spin-coated devices in order to make devices rapidly, to assess compositions or charge transport layers. But at the end of the day, we're interested in using some form of scalable manufacturing. And the one that we're working on most is spray coating, spray with plasma, as I'll mention. And I'm going to show you the cost benefits of being able to do these kind of scalable processes like spray processing. And doing it in open air means you don't need to pull a vacuum. So there's a significant improvement in the cost basis for doing it this way. This is some early work that we did showing scalable manufacturing. This is 30 centimeters by 30 centimeters. This is a high quality perovskite layer that was made in 90 seconds. So we want fast, scalable manufacturing. And this is what you're able to achieve using those techniques. Okay, so after many years of research and three big programs supporting the work, this is where we are currently. Every one of these stations here involves the scalable manufacturing of everything starting from the initial ITO. Right, now you might think, why on earth would you want to put ITO on glass? Because you can buy it from China suppliers and it's not expensive. But it turns out we can actually make ITO on glass fast, cheaper than what we can buy it from suppliers, and the quality of the ITO is better. So we can make ITO, and we do it, by the way, in open air. So not a vacuum process. We then put the whole transport layer on, again with a spray process. We put the perovskite on with a combination of spraying and then plasma curing. We then putting on the final ETL and top electrode. This ETL has been a real challenge. We spent a lot of time working on that. To do that in open air is not easy. And then at the end of it all, we can actually put a barrier on top using the same spray plasma process. On top of a perovskite cell, we can put multiple layers of dense silica and organosilicate layers that provide protection for the solar cell. Okay, so we can do it fast. Turns out that the combination of spraying and open air plasma allows you to both spray the precursor solutions down quickly, and using plasma, you can anneal them to produce high quality perovskite very quickly. And so here we are here, this is from a publication a couple of years ago, and this is comparing our work at over 10 meters per minute production compared to everything else that we could find in the literature, and even speaking to some startups. So we can go really fast. Again, it's because of the ability to both deposit and cure very rapidly. Many of these methods here, you might have initial fast application, but then you have much slower annealing. And the cost of being able to do it fast and in open air is very, very significant. So you're going to be seeing quite a bit of our cost modeling. I never really wanted to do cost modeling, but we were required to do cost modeling, and we've done this, and it's a validated cost model now with NREL over more than 6 years. So we think it's very accurate. It's benchmarked against silicon, polysilicon, and even some OPV. And you can see here the benefits. Now, this is the device production cost. It's not the full module. I'll talk about full modules later. So this is basically the cell production cost. If you can do it in open air and you can do it rapidly, we are at a fraction of the cost per square meter compared to silicon and compared to OPV. This cost model is going to be important in the message that I have today. Okay, so let me say something a little bit about the plasma systems that we use. These are all open air plasmas. They're not in chambers, and they're jet plasmas. So we either use a capacitively coupled system or blown arc discharge plasmas to produce a plasma and then have a plasma jet, which has all of the plasma species in it, emerge from the bottom of the jet. These capacitively charged systems can be run with a number of different gases. Of course, helium will never be a manufacturing gas, so we're usually interested in just nitrogen and sometimes argon. This can be run at very low temperatures, slightly above room temperature, but normally we are operating at between about 100 and 250 degrees Celsius. These blown arc discharge systems operate at slightly higher temperatures, and we operate these almost exclusively with a nitrogen plasma gas, not in a nitrogen environment, that's regular air, but the actual plasma gas. But these can actually be run with just regular air as well, taken out of the building supply. So these are commercially available systems. They're typically made for surface treatments and not for deposition. So part of the innovation in the work we've done, this is now going back over 20 years, has been using these types of jet plasmas to do deposition. And to do that, we actually inject precursor species either into the afterglow of the plasma, or you put them down first and then use the plasma to cure them subsequently. So what's in these plasmas? Well, there's three main sources of energetic species that are available in the plasma. The first and the most obvious, of course, are the radical and ionic species. That's part of what you're producing in a plasma. And if you're producing a plasma with a nitrogen flow, then of course you see a lot of nitrogen-derived species in the actual plasma. But as soon as the plasma jet emerges into the environment, then you produce a lot of species that involve nitrogen radicals plus oxygen radicals plus other species that are derived from the environmental interaction. And then there's even further species that are produced when these interact with the precursor solutions themselves, because there's organic components, there's solvents, etc. The other component of the plasma is UV light. And this is actually really important. It's deep UV. There's strong absorption of this UV light typically by the solvents. So we can drive out solvents very, very rapidly with the UV. And then, of course, there's heat. Now, we don't want too much heat, but typically, if you ramp up very quickly to around, as shown over here, to around 240 degrees Celsius, and then cool down, this is the process window in which we would operate. We use open-air mass spectroscopy to actually measure the radical and small molecule species in the plasma, and we do optical emission spectroscopy to actually measure and characterize the optical emission in the spectra. And that depends on the gas. And it's complex because there's a lot of complex electronic transitions that are occurring in the plasma environment. So all of this are things that you need to basically be able to control and be able to characterize in order to have a stable process environment. So there's lots of processing parameters, as you can imagine. There's gantry speed, heart rate, substrate temperature, spray plasma distance, precursor concentrations, type, solvent, spray height, spray power. This is a wonderful set of parameters. And of course, if you're thinking about it, it's a lovely area to do machine learning. And we've done that, worked both with our program at Stanford, and we've also worked with MIT over the years on developing some machine learning to optimize these combinations of parameters. And then, as I've already mentioned, we use the ultrasonic sprayer and then the perovskite, the plasma to actually cure the films. So here's an example of how it works. This is a substrate here. This is about 20 centimeters long, 2 centimeters wide. Here is the ultrasonic spray nozzle. Here is the plasma over here. And so what you'll see is that this is going to come down, deposit the precursor solution, which you won't see because it's transparent. And then the plasma will come along, and you'll see in real time both the deposition and the full curing of the plasma. So no subsequent processing is needed. And that's it. That's produced the perovskite in that one single pass. So we have no restrictions on this length here. We have another system where we can go over longer distances, but you can see that it can be done very, very quickly. Okay, so we've studied this for a long time, and one of the things that we did was to take this whole plasma system up to SLAC, the linear accelerator complex, and actually do in situ wide-angle X-ray scattering. And you can see here is the result. This is the Q vector over here. Here's time. This is in seconds. Here you can see the substrate, which is showing an ITO peak, because it's an ITO-coated glass. And here we spray on the solution, and you can see that the ITO peaks become less apparent because there's now a precursor solution. And this is when the plasma arrives. And you can see that the plasma then produces, as we see in these distinct perovskite lines, the perovskite phase. So here plotted is the normalized intensity of these different lines. This is the 110 peak, this peak over here. And you can see that starting here is when the processing with the perovskite actually, or the plasma begins. And you can see within roughly just slightly over half a second, we've produced a full perovskite layer. There's interesting things that you can discover here. There's intermediate phases that form, but those basically go away and you're left with the pure perovskite. So we're able to make these very large cells, as shown over here. They can then be diced and serially interconnected with using laser dicing procedures. And so we can go from, relatively small cells, as shown over here. Of course, as many of you know, most of the perovskite work that you see is done on very, very small cells. 0.15 centimeters, for example. So this is already a slightly larger cell, but here we're getting into the typical size that we like to make to do most of our work. And one of the interesting things that we found with this processing is that it's relatively insensitive to the relative humidity of the air environment. So if we use a spray with a normal air anneal, similar to what you would do with spin coating devices, then you can see these are the devices made in air with increasing relative humidity, and there's a penalty in terms of efficiency. And yet making the same devices, same composition, with open air plasma, with increasing efficiency, we see no penalty. And the reason for that is that you're forming the perovskite in such a very rapid fashion. Other advantages that we've noticed in the plasma-produced perovskites, one of them is that the stresses in the perovskite film are reduced. Now, I don't know if you've ever done this, but if you make a device like a perovskite device, you can measure the stresses that are in the film by measuring the curvature of the substrate. And that can be done very accurately. And you will always find that there's stresses in the film. And in the case of perovskite, this is not a good thing. It's not a good thing in OPV either, because they're mechanically fragile. And so here's a device that's spin coated with a normal procedure and annealed. And you can see that we're measuring stresses in the perovskite film here on the order of 15 megapascals, which is quite high. If we make them with the plasma process in open air, you can see that depending on these are the conditions, the duty cycle, the power of the plasma. Depending on the duty cycle and the plasma power, we can drive the stresses down to very low values. So we can make less stressed films, which is a big deal. The other thing that we found that was very surprising was that the fracture energy of the perovskite layer was significantly improved. This is an area we've published quite a few papers, is because of the interest. Mechanical stability, one of the key metrics for mechanical stability is the fracture energy. This is in joules per meter squared. And if you measure it for a typical spin-coated device, it's hovering around about 0.5 joules per meter squared or less. I'm going to mention what that means later. But when you make it with the plasma, we get a 10 times increase. It's still low, but it's 10 times better than being very, very low. We think this is related to the grain boundary, the nature of the grain boundaries that are formed, which, by the way, also affects the carrier lifetimes. So to put those numbers in perspective, here's the fracture energy taken from studies that we've done over many years now, where we compare the fracture energy of perovskites, which are shown over here, to organic photovoltaics, which are over here and a little bit higher. SIG systems are right around here. Silicon PV is up in this region over here. Structural materials are up there. So the fracture energy, you guys are a material science and mechanical engineering community, engineers, so you know what's the fracture energy of the steel support posts of the chairs that you're sitting in. Come on, guys. Come on, City University of Hong Kong. You've got to know this. It's maybe 30,000 joules per meter squared. That's why you're not worried about falling down. So the steel posts have fracture energies of 30,000. This is just 1,000 here. So glass, which we all know is fragile and breaks easily, has a fracture energy of 10. Perovskites have this fracture energy of about 0.1 to around about 1 joule per meter squared. So they're extremely mechanically fragile. When I worked in the OPV area and we had measured this data here, I used to say to people in talks, if you breathe on it, it'll fail. For perovskites, I say, if you look at it, it'll fail. I mean, this is very, very fragile material. So one of the important things is to think about how do we design with fragile materials. Now, perovskites aren't the only fragile materials. The batteries that you have in your cell phones are fragile materials. They contain liquid electrolytes. They have to be mechanically supported and shielded from the outside world. And so that led us to this work, which we published a number of years ago, where we said, could we make perovskite solar cells like the compound eye of a fly? So each one of these little eyes is very, very fragile, but they're protected by this organic wall, this sort of hexagonal scaffold that's protecting the cell. And here's sort of an artist's impression of what that would look like in a solar cell. So we did this. We actually used the scaffold material we used as just a regular photoresist. And so using photolithography, we created these scaffolds, and then we filled them with all of the usual layers that you would find in a perovskite cell, including the charge transport layers. We used a spray process to actually fill them, anneal them, and then put the top electrodes on. And here's an Elbeck image of the operation of these scaffold reinforced cells. And what you see is that in each cell, you see a high current as the laser scans over the cell. So it worked. The problem, of course, was that any photons arriving on the scaffold would be lost. So what we wanted to do next was to think about designing corrective optics. But before I tell you what that was, look at the benefit here. So here are perovskite cells. This is the fracture energy, the mechanical stability as a function of efficiency. You can see here higher efficiencies for perovskite cells, but lousy mechanical stability. With OPV, you can get much better. It's an organic system, so you can get better, still not fabulous, but you can get better mechanical stability, but the efficiencies were low. And what these scaffold systems allowed us to do was to move way into this region over here to produce these cells that were both efficient and much more fracture resistant. The key, though, was to correct for the loss of photons that arrived and landed on the scaffold. And we did that by actually making these corrective optics, which would be sitting on top of the perovskite cells. So any photons arriving anywhere here would be scattered into the cell. And in fact, there was some neat innovation in this area. We realized quickly that it would be better to make the optics first and then put the photoresist on top of the optics and then do the exposure for the photolithography through the optics that we had already made. So we had perfect registry of the optical corrective lenses with the underlying cells. And yes, again, part of a longer story, but if you look at the PCE here, and as a function of the scaffold area, anything lying on this line over here means that you've recovered all of the photons arriving on these cells. And in fact, there were designs that we could show and that we built, this is real data over here, where we could get perfect optical collection of data. So we were very excited about that as a potential way of designing with fragile materials. I still think to a degree that this is a necessity for perovskites going forward. Not necessarily that specific design, but I'll talk about another one that we're working on as well. So here's another advantage of this is rapid spray plasma processing. As opposed to normal devices made by spin coating and annealing, is that we get higher luminescent yield. And that's shown over here, and we've seen this repeatedly. We also see improved carrier lifetimes, significantly improved carrier lifetimes that now are on the order of a microsecond, which means that you have much longer diffusion distances. And that got us really excited because, unfortunately, the diffusion distances for perovskite, unlike silicon, are actually quite small. So that's why we typically have to make planar cells with transport layers on each side and not full back contact layers. But if you can make the perovskite to have much longer carrier lifetimes, then you have the opportunity of actually making an all back contact cell. So that's something we've been doing. We have an active program on this currently, using a microgroove concept, and this just is showing here again the ganged deposition with ganged ultrasonic spray systems, and then the plasma processing of a fully flexible microgroove system. And that looks a little bit like this. There's microgrooves that are formed on the substrate, and the microgrooves have a opposite charge transport layers on each side of the groove. And so then the back electrodes and all of these can be connected on the back side of on one side, and that doesn't require you to have this the typical planar cells. So this is work that's underway at the moment. It's working well, and again, the advantage of these all back contact cells also is in terms of improved stability. Things like cracking of the perovskite layer itself, which is one of the ubiquitous failure mechanisms, is not as prevalent. Okay, so we can make generally high-performing cells. You can see this is some work here showing around about 19% or so efficiency cells. These are large cells, 10 centimeters squared and above. And these are inverted perovskite solar cell records made on very small devices over the last number of years. And this is our work here, inching up to similar numbers, but with much, much larger cells. Okay, other aspects that we've been working on in the overall manufacturing of these cells has been the laser scribing in order to make serially interconnected cells. I'll maybe just briefly mention this. You can't just keep scaling the width of cells. I mean, ideally, you'd love to do that, right? If you just make them as wide as possible, that would be great. But the problem is the resistivity, particularly of the ITO layer, will eventually start to really hurt you. So you can see the power loss here plotted as a function of the active width starts to go up quite dramatically with increasing width. So the better solution to this would to be make monolithically integrated serial cells that are connected in this fashion over here. The problem with this is that you have to do laser or other mechanical dicing of the systems. So there's a P1, a P2, and a P3 scribe that needs to be made. If you're not solar cell people, don't worry about it. It's just that you have to partition these cells and then fill them with materials in order to get it to work. Well, it turns out if you look at the total loss, there's geometric losses associated with the size of these cells and resistive losses. And when you look at the total loss as a function of the active width, you can see that there's optimal places shown here with these X's where making cells of this size would have the least amount of loss. And so to do that, we use laser scribing. Now, the normal way to do this kind of scribing is with several different lasers in which you produce the P1, then the P2, then the P3 laser scribing from different directions. So what we've done here is to develop, this is again me saying we, it's really not me, it's my students, but particularly Austin Flick, is to produce a single back laser scribe. So here's an example of a typical ablative scribe coming from the top. This is, which scribe is this? This is it should say it somewhere here, a P1 scribe. And you can see that the problem is that as you ablate the material, this is just the height. So this is digging down through the layer, is that you produce these heat-affected zones on each side, these damaged zones on each side of the laser scribe. So what we've done here is to develop an indirect laser scribing method where we actually use the laser from the back side of the cell, and using the same laser for all three scribes, P1, P2, and P3, we can produce the scribes with this indirect liftoff method where you can see the scribe is now this really beautiful, clean scribe, as opposed to a direct ablative scribe where you have all of these damage effects on either side. So this is actually something we just recently had a patent issued on. This is the first patent I've ever written with a student where all 14 claims were allowed. For those of you who've done any work in patents, you know that you're very proud of your invention and you write up all the claims and you send it off to the patent office and they say claims 1 through 5 are disallowed, claims 6 through 10 are disallowed, and claims 11 through 15 are disallowed. So basically everything is disallowed. Then you have to go and argue and fight and complain and see if you can get some of them allowed. This was the first time where everything was allowed. So we're very happy with this particular scribing method because it can be done quickly. It can be done all from the back of through the glass. And let's see here, there's a plot here showing that in general, this is some of the cells that were made in this particular study. This is a number of years ago, where the devices and modules actually showed very similar efficiencies. Normally, when you do the dicing, the scribing operations, you see a loss in the module efficiency. Okay, so last two topics, but they have to be done together, and you'll see why. The other major challenge for perovskites is stability. Manufacturing is one. How do you do it? How do you do it cheaply? The other one, though, is stability. As I've already mentioned, they are mechanically incredibly fragile. They're also unstable for other reasons that I'll mention in a little bit. So I'm going to talk about stability, but I'm going to talk about it in the context of techno-economic modeling. Okay, so here's the typical process line that I've talked about before, and we have developed over more than 6 years now a cost model that's very, very complete. It includes all material costs, utility costs, labor costs, CapEx costs, everything is included. And here is the full open-air perovskite manufacturing of a module, which includes absolutely everything, from glass through ITO production, all the way to J boxes at the end. So everything is included here. I mean, including things like leasing of floor space, depending on how many pieces of equipment you need for the process line. And what we're doing here is comparing the open-air plasma processing with conventional perovskite manufacturing. So this is when you're having to do anneal steps and when you're having to do very controlled environmental processing. And you can see that in the open-air process, things like the ETL layer, the cost, if you have to pull vacuum or do other forms of evaporation, is significantly higher than if you can do spray processing in open air. So, again, ITO sputtering is much more expensive compared to being able to do it in an open air environment. So there's a lot of advantages here, and it allows us to understand the module costs, and we can do it also at production scale. And, as you, of course, make more and more, and you're doing it at the same speed, you drive down the costs, but you do eventually get to a place where you start having an inverse scaling with cost, because you have to start buying more equipment, for example, and operating more equipment to keep up with other faster manufacturing processes. So there's some sweet spots here that we can see as well. So here's a very important plot. This is an LCOE calculation, so levelized cost of electricity, in cents per kilowatt hour. For perovskite modules, look at the efficiencies, 14, 17, and 20%. And here is and this is a function of the module lifetime. How long does the module last? For a 100-watt megawatt installation, operating in lovely Blythe, California. This is all manufacturing in China, which is much more expensive to manufacture. Manufacturing in California, which is more expensive than if we were doing it in China. The system has to have a 30-year lifetime. Okay, so this is the levelized cost of electricity. This is the module lifetime of the perovskite modules, but the installation has to last for 30 years. So if the module lifetime isn't 30 years, you have to replace the modules. So all of these data points over here show these are module lifetimes of roughly 5 years, but so you would have to swap them out and replace them. And these costs here include that replacement cost. And in fact, they even include now in our models recycling costs. Here's the remarkable thing. Okay, so other things that we've assumed here, T80 lifetimes in the usual way, normal degradation rates, replacement costs are included. You know, there's different tax incentives that are included in the model as well. Here's the remarkable thing. Here's polysilicon over here, the levelized cost of electricity, if this were made with polysilicon. And here you would not have to change the modules. Here it is for crystalline silicon. But look at this. With the perovskite module of only 10 years, you are already more cost effective than silicon modules. And this is the critical thing that we need to understand in terms of the required stability and reliability for perovskite systems. They are never going to last 30 years. They're never going to last 20 years. We may be lucky to get them to last 10 years. We don't have any data yet. We have predicted accelerated data, but that's not actual data. And if you talk to people at NREL, it's very difficult to get data, particularly data from startups. They don't have problems getting academic groups to give them modules to test, but all of the startups who are claiming all of these wonderful lifetimes on their websites, in the meantime, they were part of the PAC program, but have all refused to actually give modules to the program. So we don't have the data. But the point is, you don't need to survive those lifetimes. Okay, so stability. Perovskites are great, and they would be stable if you never ever put them in the sun. That's the best place to keep them in your office in a drawer. But if you take them out of the drawer, they're sensitive to electric fields, to heat, to oxygen, to moisture, and to sunlight. For those of you working in the area, you know this already. But again, I think this data helps us understand how long do they really need to survive. So this is an area we've done a lot of research trying to understand some of the fundamental mechanisms. There's many mechanisms that cause degradation. It's not just the stability of the perovskite layer itself, although, of course, as you know, those layers are unstable, they're mechanically unstable. Chemically, the cations are able to migrate. In electric fields, they migrate like crazy. Worst thing you can do for a perovskite module, by the way, is run it at open circuit under full illumination. That you have the highest electric fields and it basically shreds the device. But so looking at the different mechanisms of degradation, we have been working, and this is, again, a big area. I'm not going to talk about everything. But one of the things that we found is that if you cap a perovskite cell, just put a piece of glass on it and measure the normalized versus a normalized efficiency as a function of time. Here's the control with nothing on top. Just with a piece of glass sitting on top, you get an improvement in lifetime. Now put a weight, in this case, a weight that would give you the equivalent of 1.25 kilopascal, and you see an improvement, a further improvement. So constraining the the device and the cell has a big effect on stability. And if you look at the degradation products that are formed, and this is just some of them, you would see that if you constrain the formation of these products, which are basically voluminous products compared to the original materials, then Le Chatelier's principle tells you you will decrease those reaction rates. And that's exactly what we see. So we've been working hard in our current program to implement other forms of accelerated testing. And one of them is the so-called MAST testing. It's typically used for silicon solar modules. This is a module accelerated sequential testing. And the idea here is you have combinations of damp heat, UV aging, thermal cycling, UV aging, thermal cycling, UV aging. It's this sequence of events which accelerates degradation. And these were designed for silicon cells. Now, if you try and do this to a perovskite cell, you won't get very far. You basically degrade the system quickly. And in any event, if you were to do this entire process, it's really about 165 days of testing. We need something much faster. So we've devised a curtailed version of this, of mass testing, with essentially taking into account the stability required for the perovskite systems that we're building, but and being more practical about how many cycles of thermal cycling, what type of UV aging, and for how long we need to do it. So we developed a process now which we've cut down to about 61 days, which we think should represent around 10 years of lifetime, but we don't know for sure. And anybody who tells you that they're doing accelerated testing and this is going to guarantee a certain lifetime is simply they don't know. It's not possible to know until we actually see what the actual mechanisms are, because they're synergistic effects where one mechanism starts to affect another mechanism. Something I'm not talking about at all here is that I have a large program looking at silicon reliability. So the idea there, for reasons that I'm not completely certain of, there's a desire to be able to guarantee lifetimes to 50 years. What we find there, and with very sophisticated modeling that we're doing, is that there's very complex synergistic effects where some degradation mechanism that might be happening in the EVA encapsulation material that's used in the silicon module is producing acetic acid, which is diffusing somewhere, causing a corrosion product on a line, which is causing a gas bubble to form, which is causing delamination. Those kind of things you really only see when the technology starts to mature more. So this is our best guess for what will be needed to be stable for these longer periods of time. And we're able to show those in many of the testing that we're doing now that involves these sequential tests. We've actually some lovely recent results that actually show some of the benefits of thermal cycling. So we actually see some healing mechanisms that happen, which is quite surprising. And also the effect of UV exposures, which are typically always damaging for the system. So I'm not giving you a full conclusion on, are we hitting 10-year lifetimes? We're doing testing that should, with some expectation of credibility and confidence, give lifetimes that are on that order, but it's still not clear. But again, coming back to this picture over here, I'm going to end here by just sort of recapping and telling you that we're interested in making the entire perovskite module in open air. I think for us, that's been one of the key aspects of what we're doing. We really like to implement annealing processes that involve either the plasma-produced systems or near-infrared flash exposures. I didn't talk about this. This work has just recently been published. This was a very hard problem to solve. But again, this can be all done in open air with the same efficiencies that we would get if we were doing this deposition in an evaporator. in a vacuum condition. And so maintaining the scalable manufacturing, being able to do it fast, being able to doing it with inexpensive methods, and then also integrating a quite sophisticated cost model to show that in fact you don't need the lifetimes that we get out of silicon modules. So there's some hope. Thank you.
Okay, so thank you for the nice lecture. So now it's QA session. So any question from our audience?
I have a question on the levelized cost of electricity, and a question on the levelized cost of electricity, and whether you guys have done any modeling on tandem systems and how a perovskite, silicon or perovskite, something else type tandem. What type of lifetime do you get out of those systems?
We have not. You're asking a very sensitive question, because I have been a big skeptic of tandem systems involving perovskite. I've never understood, and this is an argument that goes back to my work with Mike McGee many years ago. I've never understood why you would take a perfectly stable silicon cell and put a perfectly unstable perovskite cell on top. And so that's for a tandem involving perovskite silicon. It's different for perovskite. But taking that tandem, where there's been a lot of work, there's been a lot of funding that's actually been put towards that particular device. I've never understood that. The motivation that people will tell you is that, well, you get a few % increase in efficiency. And that actually can make a big difference. I mean, any of the big module manufacturers would do anything. They'd sell off half their family tree for a 3% increase in efficiency. And the claim is that in terms of LCOE, the cost is not that significant. Of course, there's an added cost. It's much more complex manufacturing that's needed. And so it all sounds great. So you say, well, that's great. Why aren't we all making perovskite silicon modules? But then in terms of LCOE, ask them what lifetimes they're using. They're using silicon lifetimes. If you don't use silicon lifetimes, if you use more reasonable lifetimes, 5 years, 10 years, then the economics don't work at all. So that's where I come down on perovskite silicon. Now, if you're making perovskite, that might be a little different. The application area there would be different. You could be interested in higher efficiency, flexible systems that were easier to transport or have other advantages, be more sort of niche area markets. So that could be different there. So I have a less jaundiced view about perovskite tandems. I was hearing today from one of your faculty about perovskite organic OPV systems, and that sounds pretty cool too. I wouldn't have a big complaint about that, but I think the application there is going to be different. The minute you take a silicon cell and you put a perovskite on top, you're immediately limited in terms of where you can deploy that.
Thank you. So, any other question?
Thank you. It's a very nice talk. I have two questions. The first one is about that I thought that your dominant phase orientation is 110, right? Mm-hmm. How do you compare these 110 to that 100 phase orientations? I mean, usually we think that 100 phase orientation may be more thermostable or something like that.
Mm-hmm. Well, I mean, for the system that I showed, that was the orientation that we were producing. I mean, these are polycrystalline systems. In other work we've done, we use an identifying peak to tell us when the perovskite is formed, how quickly it's formed, and so we've not been as interested in texture, if that's the question you're asking.
And the second one is that even though the perovskite is really fragile, but but that the perovskite film during bending, the crack don't affect the performance very well or something. Because you know that the crack will not affect the performance. Yeah.
Well, I mean, engineering structures can never be built to with the assumption that cracking is going to be okay. You're right in the sense that if the density of defects, in this case cracks, is low, it may not have a big effect on lifetimes. But the minute you open up a crack in the perovskite layer, from a mechanics perspective, you are now creating stress singularities on the top and bottom of the crack. So then this leads to failure in the adjacent charge transport layer. If there's enough cracking, you eventually start hindering carrier mobility, and you're opening up fast diffusion paths. So, I don't know of a study where anybody has looked at what density of cracking you could tolerate, but it's not going to be high. And I don't think it's not a strategy that you can use and say, well, you can tolerate a certain number of cracks. I mean, coming back to the tandems, that's another argument I heard that's sort of related to this. Is people say, well, okay, well, it's a tandem. If the perovskite cell degrades, so what? You're left with the silicon cell. Well, you can't have a degraded perovskite cell sitting in an encapsulated silicon module. It's going to cause all sorts of troubles. The same way, I think you cannot tolerate cracking at any kind of level in the perovskite layer, because it will cause other problems, even if it has a little effect on the efficiencies. And that also depends on the orientation of the cracks. If this is a delamination crack, then all bets are off, because you've now lost a whole area. If it's a through thickness crack, like a channel crack, that could be a little bit different, but even there will be problems.
Yeah, thank you very much.
Okay, so any question?
Thanks you for your great presentation. There are many non-radiative paths in the practical perovskite solar cells. So is there any method to reduce the non-radiative paths in the PSC?
Yeah, well, good question. I mean, there are people working on that. We've looked at it to some extent, but I don't know of any simple, easy solution.
Okay. Thank you.
So maybe one question?
So how generally you can apply this technique to perovskite with different composition? Will their film formation properties very different if you choose different composition?
Yeah, good question. So when we do change compositions, there's an optimization process that you have to go through. So you would use different you would use different parameters, but you saw there's a huge list of parameters that you can use, right? There's speeds, there's distances, there's power settings, there's gas flow rates, there's this type of solvent can have an effect too. So, when we've gone from one composition to another composition, there is a learning process to optimize all of the parameters. And that's something that we've looked at in several studies.
We're able to integrate with this high throughput analysis for compositional scale.
Yeah. I mean, this is one of the areas where the machine learning approaches become useful. I'll tell you, the machine learning never helped us develop the process faster. In fact, it took longer to integrate the machine learning, because you have to do all the training and do things that you shouldn't be doing or aren't going to be technically feasible or practical. But and I mean, that I think this is a general comment, that for the most part, and I'm using machine learning generically here, I mean AI machine learning, they're typically very good for a process line, for example, where you have a well-trained data set that you can start using, and you want to make some variation, like change the composition. Then they're very effective at that. But in terms of the actual discovery research through the initial process, there's no real benefit.
Thank you.
Okay, the last quick question.
Thank you for the presentation. I wanted to ask, on the process of increasing the lifetime of the material, you added some layers of different material like silver and then adding the pressure. Did you see any changes in the efficiency or the working of the material after modification?
Oh, yeah. No, absolutely. I mean, one comment is yes. If you change the electrode, if you change the ETL or the whole transport layer, there is an effect. They all need to be optimized. There's a tremendous amount of work that's going on in the perovskite community in general, in terms of interface engineering, in terms of 2D perovskite layers, and all sorts of modifications to compositions. As you saw through these are slides that I've developed over years of working in this area, so sometimes the structures change. What we have done, though, in general, is to keep our stack structure as simple as possible. So we're not doing all the tuning to get to super high efficiencies that you sometimes see. I mean, there's a bigger cost penalty for doing things like that. So we try to stay at more simple structures without any added intermediate layers, and with keeping the charge transport layers, for example, as simple as possible. But yeah, if you do change any of those things, it will have an effect on efficiency.
Thank you.
So let's thank you, Professor Doscott, again.
Thank you.